Hello and welcome to your lecture on the Earth's interior. So this video is just going to walk through the PowerPoint. I still suggest that you download the PowerPoint and kind of go through it, but I'm going to try and touch on most things. So we'll try to keep this, I always say this, try to keep this relatively short, but honestly, if I'm going through all the content in the PowerPoint, it's probably going to be a good 25 to 30 minutes, which if you think about it, it's pretty short, being that if we were in class, we would spend probably a week on the Earth's interior, and that would probably be a 2.5 hours. Hour and 15 minutes twice a week is usually what we schedule for the lecture portion when we're in person. So, of course, we would do other things in class. But so I guess I'm trying to convince you that a half hour is short. So you can watch the video in chunks if that's useful. But so what we're going to do is just kind of go through the information here. And so the reason that we have to learn a little bit about the Earth's interior, of course, is because we need a little geologic background. And although some of you may have taken some geology, this class does not require that. So there's no prereq. And so we do need a little information, some basic stuff, so that we can apply it when we're looking at the hazards. And so one of the things we want to do is figure out, how the interior of the Earth looks and works, because of course those things affect how the surface works. In particular, we'll talk about plate tectonics and things like that, and there's a relationship there for sure. Earthquakes and volcanoes, all related to how things are happening and working inside the Earth. So useful to know for our future. So as you look at this first slide, you can see that there's a couple ways that we can break down the interior of the Earth. And so the first and most basic way is just to do the crust, mantle, core story that you see over here on the right-hand side. And when we do that, we're breaking down the Earth into compositional differences. So we're going to argue that the crust is made of certain material, and that there is a boundary as we go inside the Earth where the composition of that material changes. When it does so, we're going to give it a new name, and we're just going to call it the mantle. And so then we have the mantle, and as we keep drilling down or going deeper into the Earth, we're going to come to another boundary where there is another compositional change. And we're going to give that a new name. We'll just call it the core. And so we just need those three terms to kind of talk about the compositional differences of the Earth, right? So crust, mantle, core. And that's useful. They behave in different ways, which we'll learn about in the future here and in other lectures. But the crust tends to be the brittle part, and as we go down into the Earth, the mantle gets a little squishier and it has these weird properties where it's a solid, but it can flow. And the core is actually made up of two different kind of parts, one that's solid and one that's a liquid. And we'll see that that impacts what's happening inside the Earth also. And so as you go through the PowerPoints, there'll be some links here that just give you some additional information you can take a peek at. It's kind of, similar to what I'm explaining here, but sometimes there's different animations or things like that, so you can go ahead and take a look. And so the other way that we can differentiate the interior of the Earth is basically how those layers or how the material behaves. And that'll become very important when we talk about plate tectonics. So what we see here is a picture of the Earth here, right? Cutting, like we call these views cross sections, where we cut through the Earth. Now, I fibbed to you just a little bit because if you look at the picture here on the right, you can see that there's two types of crust, and that is true. There's the continental crust and the oceanic crust. Now, those are composed of different materials, but if we go below them, there is a boundary there that separates their compositions from the mantle compositions. So this boundary that I'm going to draw with my cursor right here below the ocean, and it gets a little deeper here below the continent because the continental crust is thicker. That boundary is the separation between the crust and the mantle, and it is a compositional boundary. But when we want to talk about how the material behaves, we're actually going to say that we are going to take the crust, and it doesn't matter if it's the ocean or the continental crust. And we're going to take a portion of the upper mantle, and we're going to say that all of that area behaves in a similar way. And that way is that it's very brittle. It's the kind of things you experience when we look at rocks here on the surface. You hit them with a rock, they shatter, they crack, they break. They deform in a brittle fashion. And so that's important. Once again, we talk about plate tectonics and other things. So the lithosphere is the term that we're giving to that area that behaves the same, that behaves in a brittle fashion. And so it includes the crust and just the upper mantle. And because it's colder, the mantle behaves much like the crust, and so it is very brittle. But beneath that, even in this figure, and I'll show you it in the next slide here, you could see that the lower part of the mantle that's below the lithosphere is hot enough that now that material behaves differently. So it is kind of weird to think about, but you want to kind of relate it to maybe like silly putty, I guess, or Play-Doh or clay might be a good one, where if I gave you a piece of clay and I said, hey, is that a solid? You would say, yes, it is. But you can deform it without breaking it. And so we would say that it deforms ductily or plastically, which means that it can bend and it can flow over long periods of time. And so the second part that we're going to identify is what's called the asthenosphere. And that is that part of the mantle that is below the lithosphere. And it's going to act like a fluid. It's not a fluid, though. It's a solid. But it can act like over long periods of time, which means it has the ability to move and flow. And so think about, like I said, a piece of clay that you could deform slowly. It has the ability to move around. So that's important, of course, when we go back to our plate tectonic story. Okay, so the next part of this kind of lecture here is going to explain kind of a little more detail. How do we know these things, right? Because we want to drill into the earth. That's how we sample things, right? We go down into the earth and we say, oh, look, at 100 feet, this is what the rock looked like. And at, a mile, this is what the rock looks like. So if we kind of drill into the earth, we can get samples and bring it back up and say, hey, this is how we know what's going on inside the earth. But if we look at it, we really can't drill very deep. There's a lot of issues with that. Technology just isn't there, and the rocks get weird as they get hot, so it's difficult to do. So if we look at this little graph here, where you're looking at is how deep we've drilled in certain locations. And so you could see that the deepest that we've gone is about 12,000, meters here. Now the average continental crust is pretty thick here. And the ocean crust is thinner, so you think, okay, why aren't we drilling there? Well, when you drill in the ocean, you have to deal with a mile of ocean water, which causes its own problems. So, although we've drilled deep here, these are on land, and so we have not been able to penetrate through either the oceanic or continental crust. So we haven't even drilled into the mantle. We have no direct sample, where we went down into the earth and got one. And if we really want to get depressed, we can kind of look at the mantle core boundaries way down here, and these are kind of the values that were in the previous graph. So we're way far away from core mantle stuff. And so here's a few little links that talk about some of these places where we've drilled very deep. And this is a ship, or what's a good word for it? Can't think of it. It's a thing that they're doing to try to drill into the mantle, and so it's a ship that's moving around and trying different locations, mostly in the oceans because it is thinner, and trying to drill into the mantle and actually get a specific piece of it, so we can say yes, we're right. Now there are some locations where we think that there's been very violent eruptions that have brought pieces from deep within the earth, some of those fragments being from the mantle, and they have been brought to the surface through a geologic event. Though, of course, we didn't go down and grab it, so we don't know 100%, but based on what we think the composition of the mantle is, it makes sense that way. So that's how we've potentially gotten some samples from the mantle. Okay, so because we cannot sample directly, how do we know what's going on down there? So we do know what's going on there in some sense because we use the energy that's generated from earthquakes. So yes, earthquakes are bad, but they're also good in that the energy that's released from earthquakes, called seismic waves, they propagate through the entire Earth, and how they move through the Earth tells us something about what's down there. Think of it like an X-ray or a CAT scan maybe of your body. Right? I don't want to go in and cut open and dig in and figure out what's going on. I want to take a picture without actually going in there, and that's what we're going to do for the Earth. I want to take a picture without actually going into the Earth. So we're going to use seismic waves. So in order to do that, we're going to talk just really briefly about two types of seismic waves that are generated from earthquakes. And we're going to talk about this certainly when we get to earthquakes, so you don't have to know all the gory details. But I just want you to understand that we use these two main waves called body waves. One's called a P wave, one's called an S wave. Both are generated when an earthquake occurs and can be recorded, as you see here on this diagram, on a seismograph. So we can record it and look at it and use that information to figure out, where the earthquake is and size and all that kind of fun stuff. But for now, what we want to do is just say, look, when we have this P wave generated, it's a compressional wave. It's super fast. But the key here is that this energy, this wave, is moving through both solids and liquids. That's useful. Now, all waves change their speed when they go through different material. The more kind of compact something is, the faster the waves travel. And the more loosely packed it is, it kind of slows down a little bit. So the speed of the wave can tell us something about the material. But certainly here, we know that we have a P wave and it goes through both solids and liquids, and that's important. When we look at our S waves, our other body wave, it's slower, but because of the way it transmits its energy, it cannot move through liquids. So solids, good, but not liquids. Okay, so that's useful when we figure out what's going on inside the Earth. So what happens when there's an earthquake big enough to send these waves throughout the entire Earth? Well, what they do is they bounce off different layers, they bend through different layers, they change their speeds through different layers, and we can record these waves. And because, yes, there's one P and one S, but once they start bouncing around, they generate lots of different waves. And people that are way smarter than me, this is what they do with their career, is they evaluate all these waves. And so the fact that it can bounce off a layer because there's a compositional change, properties of the material have changed, and it allows the wave energy, some of it, to bounce off and be recorded, and then we can figure out how deep that boundary is. In other places, it crosses over the boundary, but it changes its direction, and once again, that's related to its speed. So don't get too hung up on all this stuff. We're just trying to tell you that this is how we're looking inside the Earth using these properties of waves as they travel through different materials, right? So they refract, they reflect. A lot of this is helping us figure out at what depth do we have something different, like between the crust and the mantle, or even between the lithosphere and asthenosphere, because one's colder, more dense, waves travel faster. One's hotter, less dense, waves travel a little slower. We can even pick up those types of boundaries. So not just compositional. And so one of the ways that we determined the crust-mantle boundary was through seismic waves. And this one gentleman who discovered it in 1909, it's referred to as the MOHO, as short for Mohorovičić, I think. I always mispronounce that, but so that's the way we've determined the crust-mantle boundary, was using these seismic waves. And since then, of course, we've been able to identify much more of these different types of layers that we see at depth. Okay, and so if we just had, a Earth that was just the same through and through, we would expect something that looked kind of, like this, where the speeds would get a little faster because of pressure, but they would just show up everywhere. But what we do see is wave speed. So this is a diagram showing velocity with depth, and you can see that the P wave, as it gets deeper, gets faster because, of course, that it's more dense. The pressure is kind of crushing it together, so it allows it to go, a lot faster. But it crosses this boundary here in the outer core, and oh, guess what? The outer core is liquid. And so because a liquid is less dense than a solid, there's a big change in speed. It slows down. And of course, our S waves can't go through. There's no S waves. So how does that help us look inside the Earth? Well, let's look at, I'm going to jump through this. This is just a little diagram showing you what it would be if it was all the same, what it is because there's different layers inside the Earth, is there are these things called shadow zones. And so when there's an earthquake, these waves can travel through the entire Earth. We have thousands upon thousands of seismographs throughout the world, and they are recording when these waves kind of are, hit this location, and then we can interpret those. Now, there's a P wave shadow zone because of the change in direction of the path of the wave. And this is due to the different compositions and properties of the material. It's changing and slowing and things like that. But the thing that I think makes the most sense, so this is, working off that principle of these energy waves are moving or speeding up and things like that. But when we look at the S wave, so this one probably makes a little more sense. We said that S waves do not travel through liquids. And so when there's an earthquake, let's say up at the top here, there are no recorded S waves on the opposite side of the planet. And so the interpretation from that data would be that there must be something liquid inside the Earth that is stopping the transmission of these waves. And so this is one way that we're determining that there is a liquid outer core, a boundary. There must be a boundary between the mantle and the core. And so the idea that there's no S waves tells us that at least part of that core must be a liquid. And if you think about it, just looking at this diagram, the reason that we know the depth, like where is that boundary, is the shape or the kind of degree of this shadow zone. Imagine if I had a very small liquid core. So I reduce this circle in size. You would see that the waves would then come out and hit here. So my travel, or my, what do we call this? Shadow zone would be much smaller. So the size of the shadow zone is indicative of the size of the core that is liquid there, right? So this is how we can draw that circle and draw it at that depth and say, hey, this is a boundary between mantle and the core here is liquid, at least at this point. Now, the other thing that we talk about is that the core is also two parts. It is made of the same material, but we have a liquid outer core and a solid inner core. So how do we know that it's a solid inner core? Well, one of the ways is a P wave that travels straight through the planet and is recorded on the opposite side of the planet. And so because we know how, the distance between one edge of our planet and the other, and we have some information about what the material is inside the Earth, if it was all liquid, remember when it hits a liquid, the speed slows down. And we know the size of this thing, so we can say, oh, for this amount of distance, it's going to be slower. And then it should pop out the other side, and I can estimate how long that should take. But it arrives much faster than it should if it was entirely liquid. So what could help speed it up? Well, a change to a solid. And so because the solid is much more dense, the speed of the wave through that solid is much faster. And so my wave arrives here way faster than it should be, suggesting that there is a solid inner part to my core. All right, so this is just one way that we can use seismic waves to start to see inside the Earth. Would it be awesome if we could go down and grab a piece of it? Of course. But because we can't, we have to use this idea of looking inside the Earth with these seismic waves, right? So this CAT scan inside the Earth. And, this has been done like lots of things, right? Experiments that we do to collect data, we want to know that they're repeatable. Well, luckily or unluckily, there's thousands of earthquakes that occur. And we have thousands of pieces of data that keep supporting this idea that, hey, there's a liquid part of the Earth at this depth because every earthquake is showing at the same location. Hey, there's something solid in the middle because every earthquake is showing. Hey, there's a crust mantle boundary because these waves keep bouncing off this thing at about this depth everywhere on the Earth, right? So I feel pretty confident that we have some idea of what's happening inside the Earth there, right? And so this is kind of how we understand what's going on inside the Earth. So it's important to know, for us, crust, mantle, core, there's two parts to the core, right? Liquid outer, solid inner. This is a compositional difference, remember. And then this other difference that we're going to focus on, which is near the surface, the lithosphere, is the crust and upper mantle that is very brittle. Beneath that is what's called the asthenosphere, right? That is the gooey inside caramely kind of part of the Earth that is hotter. It is not brittle. It does not break. It is more like clay or silly putty or something like that. It is a solid, but it has the ability to move over geologic time, and that movement potentially is causing the lithosphere, the brittle part of the Earth, to move around. This is kind of hinting you into this plate tectonic story we're going to talk about, right? They're kind of driving some of this brittle stuff around, almost like a raft on water. And of course, these plates, these pieces of the Earth that are brittle are broken into pieces, and they can bounce into each other, and this is where we get collisions and earthquakes and all that crazy geologic stuff that we'll learn about in the next module. But this is why understanding how the interior of the Earth works is useful for us, okay? Now, there are a few other ways that we can look inside the Earth. Some are not as deep as, let's say, looking at the core mantle. So the one I'm going to show you here is looking at some properties of the Earth that are in the crust, potentially. And what we can do for that is we can use gravity. And so same thing. I know there's some math popping up here and there in physics. Don't get carried away. We just want you to get the concept. So the concept here is that there is a formula that says two objects are attracted to each other. There's a gravitational force there. And it's based on the mass of the object and the distance. And we can measure some changes in that, right? So if the objects are closer, there's a stronger attraction that can be measured, of course. And if they're farther away, there's a weaker attraction or pull. And so that's one way we can determine size or distance, how far down something is inside the Earth. And then also the masses tell us something. So if the objects are more massive, there's more attraction, so stronger pull, less massive, okay? And so what we do is we have a tool called a gravimeter. And so in this example here, all we have is a spring with a known mass. So the mass in the gravimeter doesn't change. So when I move it across the Earth and there's something really big and heavy down there, so the mass has increased here relative to not having something. And so bigger mass, stronger pull, I get a higher gravity reading. It tells me there's something different down there. As opposed to if there's nothing, it'll tell me if there's something different like a cave, because it is less dense now, so less of a gravity measurement. That can tell us something about what's inside the Earth. Okay, and let's see what else we got. So as we go over the Earth, we can see lots of things potentially inside the Earth. So sometimes these things are called anomalies. It just means difference in gravity. Oh, let me jump back here real fast, sorry. And so we can find sometimes resources or deposits and things like that have been concentrated. Certain rocks are heavier than others. And so we can, determine that there's something big down there, at depth. And sometimes we can see different rock types related to volcanic events or old volcanic events, like hidden. It's been eroded away. We might see something like that. Or we could see, some changes in the structure, right? So same thing. It's really based on rock type. There's things called salt domes, which are very weird, I know, but you get oil and gas there sometimes. So these big salt deposits are mobile inside the crust. They can move up and distort the rocks around it, but they're not very dense, so they might show up as an anomaly. Or here where we have some old buried faults, because the rock that filled this kind of depression here is a lot lighter than the rocks around it that are very hard, like granites or things like that. And so it would indicate that there maybe is a structure down there that we can investigate. So we can use a gravimeter to measure gravity, and that can help us determine what's going on at depth. So that's another way we can look in the Earth without actually going down there, right, and drilling into it. And then, let's see, there's only a few other things we want to talk about. Thank goodness, I know you're saying, but that we have to know about what's inside the Earth because it drives some of the information and data that we're going to use to interpret what's going on our planet and why. And so the next thing is the Earth's magnetic field. And once again, this is a complicated idea. We're going to kind of really gloss over the details and just say to you that there is a magnetic field because it can be measured, and it does kind of mimic what's called a bar magnet. Imagine if there was a bar magnet, like in this picture, running through the Earth with a north and a south end to the magnet. There are these lines of force that are moving from one end of the magnet to the other. If you have taken a physics class, or if you've looked at something like that where you've done an experiment and put some metal filings, you can see them align. It's the reason that your compass needle moves around on your compass that can tell you which way is north. And so we know that that's there, and that's useful for a variety of reasons. We think that it is being generated because of this liquid outer and solid inner core that's made of iron and nickel. This kind of motion of the fluid moving around a metallic object. So metallic fluid moving can generate electric field, which then generates a magnetic field. And this is why we have this magnetic field, which is good, of course. It protects us from horrible rays from the sun and radiation and all those kind of things. And as long as we have one, we feel pretty good about that. There is some evidence that the magnetic field moves around. And just as a side note, remember the magnetic North Pole is not the same as our geographic, and that is because the magnetic pole can wander around and move a little bit. So the geographic pole is one that's based on the spin of the Earth, and it's kind of a stationary object, whereas the magnetic pole moves around over geologic time. And it not only moves around, there's evidence that it has flipped in the geologic past, and that means north was south and south was north. So we have evidence in the rock record that tells us that. And of course, we don't know specifically how fast that happens. Does it happen all at once? Does it happen in a day? Does it take 100 years, 1,000 years? It's more difficult to pin that down. But that flip is something that we can see recorded in the rock record. That's also some data that's useful for us to understanding how our planet works, and useful for understanding plate tectonics, and useful for interpreting earthquakes and volcanoes and all those kind of fun things. So, how does it work? Once again, we're just going to gloss over the details. Don't freak out, but some rocks, and in particular igneous. What's an igneous rock, you say? It is a rock that forms from molten rock. And so that is the definition. If it's molten and it cools and crystallizes, voila, it is an igneous rock. Now, a lot of igneous rocks have minerals in them, specifically magnetite, and as these minerals form, they actually align themselves to the current magnetic field at the time they cooled and crystallized. And they're oriented a specific way. We can measure that. So, of course, if it's opposite of what our magnetic field is today, this is evidence that there's been a flip. And also the fact that it's oriented, and you can see in this picture, it's got this angle here, right? It's not flat. That is based on its location. Weird, I know, but the magnetic field lines are different in different locations. And so if you're near the equator, they're more kind of pointing parallel to the Earth's surface. And as you get closer to the poles, they tilt more vertically. And so based on how they're tilted, we can tell where this rock cooled and crystallized. Did it cool and crystallize near the equator, or did it cool and crystallize up north or down south? And so this is why understanding the magnetic field inside the Earth, yes, and the fact that it can be recorded in the rock record, useful, so that we can use that to interpret what's going on our planet and all that kind of good stuff. So, how does that help? Once again, I'm just going to throw out some stuff that we're going to talk about in the future. We're really prepping you toward the end here related to plate tectonics, which is coming up next. And one of the ways that we figured out that there was this idea of plates, of these rigid parts moving around, was that we had this flip in polarity that we could observe in the rock record. There are places on the planet where brand new crust is being created, oceanic crust. And so as it's created, it cools and crystallizes, and bam, it cools and it records the polarity of our magnetic field. Well, over time, long geologic time, millions of years, if we look at this kind of tape recorder of new crust constantly being created, we see a flip. Boom, 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 boom. And of course, we have these areas where the creation of new crust then pulls apart, so new crust can be formed. We get this kind of striped effect or mirrored effect, and that is a big clue into this idea of plate tectonics. And so that'll be discussed certainly in the plate tectonic module. I'm just kind of teasing you a little bit with that information. And let's see. We already talked about this, so I'm going to jump through this one. And then the last thing I'm going to show you is related to plate tectonics, but more ways we kind of figure out what's happening inside the Earth. And that is, we do look at these earthquakes, not only the seismic waves, but this kind of map view that you're seeing here is showing the epicenter, the location where the earthquake first originated. And I know it's hard to see in this map view, but there's different depths here that we're seeing on the map of locations of earthquakes. And so these blues are much deeper over here, they're much shallower over here. It's telling us something about what's happening at this particular place, which is a boundary between two plates that are crashing into each other. The brittle lithosphere, remember, the brittle lithosphere is breaking when we apply stress to it. That is an earthquake. Remember, the asthenosphere, which is below the lithosphere, can't break because I try to break my piece of clay and it just oozes, it just moves. And so I only get earthquakes in the brittle part of my planet, which is the lithosphere. And so when I look at a side view of that exact map view we just looked at, and we plot those earthquakes, stop. We don't want her to speak, and I don't know if I can change it. Oh, crap. Okay, so you're going to hear her speak, and I'll let her finish, I guess, here.
Anchorage, Alaska, clearly shows the inclined fault plane separating the North American and Pacific plates.
Okay, that's enough out of her. I muted the other one, but apparently I can't do it while it's in my PowerPoint slide. But okay, so what are you seeing here? You are seeing a piece of the lithosphere that's up here typically actually moving, being pushed into, what's this stuff here? The asthenosphere. This is the clay. This is the gooey part that we said can be pushed out of the way. And so this is a concept that, once again, we'll talk about when we get to plate tectonics next week. And when two plates run into each other, what can happen in some cases is one plate is actually shoved beneath the other. How do we know that? We know that by this right here, because as we push this brittle thing into this non-brittle thing, the non-brittle thing isn't breaking, but this brittle piece is breaking here. Now, there's a plate up here that they haven't defined because they're not mapping the locations of the earthquakes. That would be brittle also. So I should see lots of dots up here. This is my brittle lithosphere. But this part of the lithosphere is being pushed into this part here. That's this clay, this gooey part, right? Because it can't break. I don't get any earthquakes there. And so it nicely defines this brittle part of the plate that is being pushed down into the mantle. And this is more helpful information for understanding plate tectonics, which helps us understand where earthquakes occur, which helps us understand where magmas and volcanoes occur. Super important. So, how do we know? We look inside. How do we know? How do we do that? Seismic waves, in this case, epicenter locations, understanding the magnetic field and how that works. All of these pieces help us see inside the Earth. And so lastly, another example. Here's a nice diagram that shows two lithospheric plates running into each other. And we see this pushing of one deep into the Earth, into the part of the Earth that's gooey, clay, silly putty, whatever you like, okay? And so the only thing that can break is this brittle piece. Not here, not here. And so that's what you're seeing in that little dot plot from the previous slide. But one last trick up our sleeves is we can look at the temperature difference of parts of the Earth. This thing, this lithosphere, is colder and it is near the surface, but the stuff deep in the Earth is much hotter. So I push this thing into this hotter part down here, and it's still retaining some of its temperature before it gets heated up by the surrounding mantle. And so it's still cooler. And so now I have this blobby thing that's representing this piece of the Earth, the lithosphere, that is being, what we're going to learn is called subduction. So that is getting pushed down into the mantle here. So that's another way that I can see inside the Earth. And of course, that can help me understand how the Earth's working, which can help me understand how the surface of the Earth is behaving based on this moving of plates, this magnetic field stuff, these different properties of the mantle and the crust and the core. All that stuff is putting together all those pieces to understand Earth movement, earthquakes, and for us, like I said, lots of hazards. Specifically, the earthquakes and volcanoes are the biggest ones, but all controlled by kind of how our Earth is behaving, this dynamic planet we live on. So, don't focus on the gory details. The big picture here is lithosphere, asthenosphere, crust, mantle, core. How do we see inside? Seismic waves moving through the Earth tell us something about that. How else can we see inside? Gravimeters. What about, recording the magnetic field? Oh, we can do that. How does that work? Well, the magnetic field is controlled by the liquid outer core, solid inner core. We can record the polarity in certain igneous rocks. That can help us piece together how the Earth is moving on the surface. Okay, these are the things, you don't have to, figure out exactly how the things are recorded, just that they are recorded, right? So we don't want to go too in depth, but we want to expose you to some of these techniques that we're using to understand the inside of the Earth. Okay. So there is a little chapter 2 to read in association with this, and hopefully when you read through that, it'll tie together kind of all the stuff we've talked about here and give you some additional stuff. So make sure that you're taking some notes potentially while you're watching this, while you're reading, so you can study those before you take the lecture quiz. Okay, it's long, I'm sorry, but sorry not sorry. That's how it goes. I mean, because of a lot of information that we would do weekly if we were a live class. And of course, for you guys, unfortunately, or not unfortunately, I shouldn't say that. This is just, it's a lot of information. And if you're doing multiple modules, it can be a lot. So take your time, ask questions if you have any issues with the content here. Reach out to me and I will help you out.